Bismillahirrahmanirrahim. Let's see if the voice is coming or not. Hello, hello, hello. Hello, hello, hello. Oh, hello. Yes. So let's start the today's lecture. Now, this lecture is about microwave resonators, and I sent you um, the the notes so you can look at them. Oh, sorry. Just a second. Okay. So so a microwave resonator is a device which is strong at some frequencies. So I will just put a circuit here. Like for example, this circuit. This is an RLC resonator. So what will happen if we put a voltage here and there is an output? So at some frequencies there will be a large amplitude, which is F naught. At some frequencies the amplitude will be nothing. So maybe we call it F1. So this is a resonator. Now, how the the uh, the frequency versus voltage will look like this. So if we have frequency here, omega, and here if we have the output, so it will be, for this circuit, it will be typically look like this. So at the resonant frequency F naught, I have, so this is I call F1 and this is F2. So now this type of resonator is the opposite. In this, at F naught, I will see very small amplitude, and at F1 and F2, I will see a large amplitude. So this is a typical example of a resonance. Um, Now another circuit which will be, it will behave like that is, so what will happen at the resonance? At the resonance, j omega L will be equal to 1 over j omega C. So this becomes a short circuit, like that. So it's like a short circuit. So all the voltage at resonance will go back and nothing appears here. Similarly, another circuit like that, another resonance will be a parallel resonance. So this is the first example. The second example is the parallel resonance connected in series, which is like this. So I have input here and output here. So when this condition, which is called the resonance condition, it is satisfied, uh, this will be like an open, because all the current will be inside. So nothing will come out. So again, the characteristics will look like this. This is my omega, this is my voltage. Resonator connected in series. So I have, like, all these are resonance circuits. So L, C, and R, and I have V input and I have V output. So now uh, at the resonance, again, if you look at it here, at the resonance, uh, Now this is a circuit which, if you look at the impedance here, Z input, it is something like this. It is 1 divided by 1 over R plus j omega C plus 1 over j omega L. So when this condition is satisfied, I have this becomes 0, and this is 1 over R. So this becomes a high number. So it is much, much larger than 1. So which means that nothing in this direction, there is a very high impedance. So all the voltage will go on this side, all the power. So it will, the voltage versus frequency will look like this. Fourth example is series resistance in parallel. Parallel, series, yeah, series in series. So it is R, L, and C like this. So I have R, L, and C. Now at the resonance, everything will go on this side. Circuits. Now these resonance circuits are the resonators are very important in microwave because they are used in applications like filters, amplifiers. So filters, as you saw it in the design of the band pass and band stop filters. So it is used in filters. They are also used in amplifiers and oscillators. And microwave oven is one of the example. In the microwave oven, there is a microwave resonator inside. So so it resonates on one very high strong frequency. Now, when does this resonance happens? When do you see this peak or this low in the output characteristics? This happens at the point when the magnetic energy is equal to the electrical energy. So I can write it here. Resonance condition. So this is the condition when I have OM, WM is equal to WE. So magnetic energy is equal to the electrical energy. And we will look at some of these parameters in the next part of the lecture. So this is the condition, and this condition also comes from this condition. So at that point, the reactance, inductive reactance, is negative of the capacitive reactance. So that is why I get the resonance. Now let us look at it in more detail. And what I will do here is as an example, I will analyze the series circuit. I will analyze the series circuit here. So the series circuit is like this. I have R, I have L, and I have C. R, L, and C, and this is my input impedance. So what I will do here, I will calculate the parameters which I need to define are the WE, WM, input impedance, the resonance frequencies, which is the point of resonance in frequency, and another very important parameter which is called the Q factor, the quality factor, and the bandwidth. these are the very important parameters of a resonator, and we will define all these parameters. Now let us first look at the easiest parameter, which is the Z input. Z input, as I can see from here, if I look in this direction, the the impedance by looking at here is R plus inductive reactance plus capacitive reactance. So this is a very simple rule: R plus j omega L plus 1 over j omega C. So this is my input impedance. Now to calculate the energy, I use the very uh, well-known relation, which is given by the energy of any circuit in any circuit is given by the total energy, which is P input, and that is equal to 1 over 2 VI conjugate. Uh, and this energy is equal to the general form of energy. This is the P in, and the energy which is used by the power, which this is the power which is coming inside, and this power is equal to the power used by the circuit, and this power is given by power used. I call it power used. This is equal to power loss plus power plus the magnetic energy, sorry, plus 2j omega magnetic energy minus electrical energy. So this is the general relation. So what I will do is I will, and in any circuit, as we know that power in is always equal to power used. So let us look at that. First of all, the power in. Now in this case, what is the voltage? The voltage is given by the current multiplied by the impedance. So this is, the current is uh, R plus R plus j omega L plus 1 over j omega C. So I multiply it here. P in is equal to 1 over 2 V I conjugate. So I conjugate multiplied by I multiplied by, yeah, so this is V. So I replace this by V, which is I. Okay, let me write it again. This is VI. So this is equal to 1 over 2 V, which is this. So I conjugate multiply, this is my voltage, and multiply by R plus j omega L plus 1 over j omega C, and this is equal to 1 over 2 I multiply I conjugate. This is the two complex number, one complex number with conjugate multiplied by the actual complex number, which is equal to the magnitude square. And then it is, what I can do here is I can take I can just put it here, R plus j omega L plus 1 over j omega C, and this is equal to 1 over 2 I square R plus 1 over 2 and I multiply j omega inside. I take j omega common, so j omega, and I multiply this inside. So I take j omega common and this multiply inside. So I have 1 over 2 L I square minus 1 over omega square C. Because of this, omega is outside, so I put omega square here, and j I put minus, and then there is 1 over 2 also here. So 1 over 2 I square. Now, in order to make this equal to this, I have a 2 j omega here. So I can take 2 more common outside. So it will be 1 over 2 I square r plus 2 j omega, and I have 1 over 4 L I square minus 1 over 4 I square divided by omega square c. So this is my power. So now this power is equal to this power. So I can know from there that the loss power is I square r, magnetic energy is 1 over 4 Li square, and electrical energy is 1 over 4 I square divided by omega square c. Now why this? Why are we doing this? Because of the reason which will be coming right now, that we need to get the other parameters which include the resonance condition and the quality factor, etc. So let me just delete this here, it here, and I'm calculating. So this is my current. So P input is equal to the P which is used by the circuit, and that is 1 by 2 I r square plus 1 by plus 2 j omega 1 over 4 L I square minus 1 over 4 I square divided by omega square c. This is equal to P loss plus 2 j omega W m minus W e. So this implies that P loss is equal to 1 over 2 R I square R. Omega m, Wm is equal to 1 over 4 L I square, and Wc is equal to 1 over 4 I square divided by omega square c. So I have these three important parameters: P loss, omega, Wm, and We. Now for resonance, I know that omega m equal to omega c, so I can make these two equal. So resonance, where omega equal to omega naught. So at this frequency, omega m is 1 over 4 L I square is equal to 1 by 4 I square divided by omega naught square c. So the current cancels here, this also cancels, and I get my resonance condition, which is omega naught square is equal to 1 over LC, which implies omega naught is equal to 1 over LC. And in terms of frequency, it will be 1 over 2 pi, sorry, square root LC. In terms of frequency, it will be 1 over 2 pi square root LC. So for any circuit, if I want to find the resonance frequency, I can just, any type of resonance, basically we will see that other resonance circuit has also the same resonant frequency. But anyway, for this, okay, now let us look at the input impedance at resonance. So at resonance, the input impedance is given by R plus j omega L plus 1 over j omega C, and this is equal to R plus j omega L plus, now at resonance, omega equal to omega naught. So this is omega naught L plus 1 over j omega naught C. So this is equal to, now let me put the omega naught here. So it will be plus j omega naught. Omega naught is 1 over square root LC, so I can just put it here. 1 over square root LC L and plus LC, because it is down, so it will be LC square root divided by JC. So one of the L cancels here. Sorry, one of, so this L will become square root. So this will be R plus J square root L over C, and this is minus J square root uh, L over C. So this is cancels and we get equal to R. So at resonant frequency, at omega equal to omega naught, the input impedance is equal to R. And this follows from this circuit, if you can look at it. At the resonance, this will become a short, and only I can see the R. So which also comes from this equation here. Now a very important parameter of the resonance, which is called the quality factor or the Q factor. So this is so the next topic is the Q factor and the bandwidth. So the next topic is because these two are related, Q factor and bandwidth. So let us first look at what is actually the bandwidth of the. So what I want to do here is, this is my input impedance. This is my input impedance with frequency. So I have an impedance like this at 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 the resonance frequency. So at omega naught, this becomes R. Now the bandwidth is the width of this resonance. And how do we calculate it? We calculate it by calculating these two frequencies. So omega 2 and omega 1. Now what are these frequencies? This frequency is the frequency at which my R increases to square root 2R. So so when the R is square root 2R, when the input impedance is square root 2R, we calculate the two frequencies. And this is my bandwidth. This is my bandwidth. So the next, now what is the relation between the Q factor and bandwidth? We will see in a few seconds. There is a relation between Q factor. Now what is Q factor? Q factor is defined as omega naught plus multiplied by the magnetic energy plus electrical energy divided by P loss. Now we know that at resonance, omega m equal to omega e at resonance. So this is either 2 omega m or 2 omega e. So I have, sorry, 2 Wm or 2 We. So I have omega naught multiplied by 2 We divided by P loss. This is also equal to 2 Wm divided by P loss, because those two are equal at resonance. All right. So let us find these two numbers. So I can just put, oh sorry, this is omega naught here. So I put omega naught multiplied by 2 We. So I know that We is given by 1 over 4 L, sorry, 1 over 4 I square divided by omega naught square C. And this is also equal to omega naught. So these two will give me the Q factor in terms of L and C. So this is equal to the magnetic energy, which is L I square. Loss is 1 over 2 R I square. So this is divided by 1 over 2 I square R. So let's see what cancels out. I cancels. So I cancels on all the sides. One of the omega naught here cancels with this. So I have two equations which will give me the quality factor. So this is, now this is 2 here, so this 2 cancels with this 2, and then 1 over 2, 1 over 2 cancels. So what I have at the end is my equation for quality factor, which is uh, divided by R. So it is 1 over RC omega naught square, and this is equal to omega naught. This is equal to omega naught. I have omega naught and then L over R. So this is the two equations for the quality factor. All right. Okay, now let us do an example of uh, the uh, what we have just some of the concepts which we have just gone through. So example one. In this example, I have to design an RLC resonator at 3 gigahertz. So this is a design of RL3 gigahertz resonance, the impedance at the resonance and the bandwidth. Now I need the bandwidth and Z in at omega naught. So what I do is first I design. So I need the values of, so I need the value of L and C. I have 1 ohm resistance, but I don't know L and C. So I know that the resonance frequency is given by omega naught is equal to 1 over LC square root, right? So I now I need to assume one of them. Either I assume L, and because I know omega, which is 3 gigahertz multiplied by 2 pi. So I know this, but I don't know both. So I assume one. So I can assume one of them. Assume L equal to 1 nanohenry, because the frequency is in gigahertz, so L will be in nano. So I can assume any nano number, any suitable nano number, 1, 2, 3, whatever, and then calculate C. So I have 2 pi f naught equal to 1 over square root LC. So f naught is equal to 1 over 2 pi square root LC, and I square it. I can delete this because I already found the Q, and the Q is given here. So so L will be C will be equal to I square it, so it will be f2 pi square f naught square, so it will be 1 over 4 pi square, and then L, f naught square L. This will be my, and this comes out to be this. If I put all those numbers, 4 pi square f naught square is 3 multiplied by 10 to the power 9 square, and L is 1 multiplied by 10 to the power minus 9. So this comes out to be, I think, 2 point something. So this comes out to be 2.814 picofarad. Now at resonance, so the input impedance is equal to R plus j omega L plus 1 over j omega C, and I can just take R plus j omega common, j omega L common factor. So here I will have 1 minus 1 over omega square LC. Now this is my resonant frequency square. So this will be R plus j omega L, 1 minus, this is omega naught square. So omega naught square divided by omega square. So when omega equal to omega naught, this is 1. So 1 minus 1, 0. So this input impedance is equal to R equal to 1 ohm. All right. Now for the bandwidth, I cannot, it is difficult to find from this because the bandwidth, I need to, what I have to do is I have to have these two, as I showed you before, that the bandwidth is actually, I need to have, this is my curve of Z input. So this is 1 ohm. So I need to have square root 2 here, square root 2R, which is square root 2 ohms. So I need to find these points. So this is my F naught, and this is my F naught 2, and this is my F naught 1. So what I did is, you can find it from the equation by putting square root 2 here and then, but that is a little bit, we will do it in the next section and get a formula. But for right now, I can use NSoft. I used NSoft. So I found that this frequency, so you can see from in the lecture notes. So this frequency is equal to 3.08 gigahertz, and F naught 1 is equal to 2.92 gigahertz. So this is, I just found it from NSoft, and the bandwidth, if I subtract these, it comes out to be 0.16 gigahertz. All right. Okay. Now this is the end of the example. So now let's go back to the this formula, Z input, and actually calculate the bandwidth. Calculate the bandwidth of the circuit. So this is what is the actual bandwidth from this. So what I do here is, yeah, so I'm here now, so I need to find the bandwidth. So I have the Z input, which is equal to R plus J omega L, and 1 minus omega naught square divided by omega square. So I continue this equation, and I put omega square, I just solve it here, omega naught square divided by omega square, and this is equal to R plus J omega L. Now this is omega square, 2 squares, and there is a subtraction, so I can just write it in the form of A plus B and A minus B. So I have omega plus omega naught and omega minus omega naught divided by omega square. Now what I assume is, this is my F naught, so I assume a very small delta. So my delta omega is equal to omega minus omega naught. So in the graph it is like that. So I have this, if I have this is my, if I have this is my graph, so this is my delta omega, which is, so if this is my graph, this is my omega naught. So my delta omega is a very small delta at a frequency of any frequency of omega, which means that I'm very close to the resonance. So if I assume this, where delta omega is a small number, this is my delta omega, and I can replace omega naught by delta omega here. So omega naught is equal to omega minus delta omega, and we will see that this brings us to a very nice approximation of the input impedance, and then we can calculate very nicely the bandwidth. So I replace here, so my input impedance is now, impedance is now R plus J omega L, and inside I have omega plus omega naught. So I have omega plus omega naught is omega minus omega delta omega, so it will be omega plus omega minus delta omega, omega minus delta omega, and multiply by omega. right? Multiply by delta omega, delta omega divided by omega square. So this is 2 omega. So this will be equal to r plus j omega L, 2 omega minus delta omega multiply 2 omega minus delta omega whole square divided by omega square. Now, assuming that delta omega is a small number, delta omega square is even smaller, so I can just go take this to 0. So it simplifies my equation. So I have uh, this will be 2 delta omega. This becomes 0 divided by omega, and this omega now cancels with this omega. So I have r plus j 2 delta omega L. So this is a very simple form of uh, the input impedance to find uh, the bandwidth. Now, as I told you before, that I will draw it again once again to because it will we need to find the bandwidth. So I have this. This is my curve. This is omega. This is z input, and this point is r. Now I need to find this point f2, for which this is square root 2r. The impedance is square root 2, and this is also f1, which is square root 2r. So my bandwidth is this. This is my bandwidth. So what I do, I put square root 2r equal to r plus j2 delta omega L, and I square it. Or the yeah. So yeah, so this is the actually the impedance. This is the because this is my magnitude. So this is magnitude. I calculate the magnitude here. So what is the magnitude of this? Is equal to the real part square plus imaginary part square, 2 delta omega L square, and then square root. So I have square root 2r equal to square root r square plus 4 delta omega square L square. Now I square the two sides, so it will be 2r square equal to r square plus 4 delta omega whole square L square, and this r goes here, it will become r square 4 delta omega whole square L square. So now this is this delta omega, right? This delta omega, because I am finding these two roots, square root 2r. So this is this delta omega, uh, and this delta omega square is equal to r square 1 over 4 r square divided by L square, right? Uh, so delta omega is equal to 1 over 2 r square over L square, right? Yeah. So now what is the bandwidth? Bandwidth is double this, because this is one side, we also there is similar here. So the bandwidth is 2 delta W. So bandwidth 2 delta W, which is equal to r square divided by L square. Now we see here that the quality factor is omega naught L over R. So from this, R over L is actually R over L. So R over L from here is omega naught. R over L is R over L is omega naught divided by Q. So my bandwidth divided by omega naught is 1 over Q. So the bandwidth is proportional to Q. So if the Q is large, the bandwidth is small. So why this is important? Why the Q factor is important? Because Q controls the width of the resonance. It controls the width of the resonance. So if I have a very large width, if the bandwidth is high, which means it is low Q. If the bandwidth is small, which is like this, so it means I have high Q. So in general, for the good filter, high Q. So if there is a Q high quality factor, that's why it is called a quality factor of a filter. Uh, that the quality factor is, if it is high, then it means that the filter is very good. It is very narrow. All right. Now let us go back to the previous question, in which we found the bandwidth to be 0.16 gigahertz. So let us put it here in our, from this, the bandwidth over omega naught should be equal to R over L, and in that circuit it was, this was 1 nanohenry and the resistance was 1 ohm. So R over L is equal to, so let us calculate that. So 1 over 1 nanohenry, and the resonant frequency was 3 multiplied by 10 raised to the power 9. Omega naught is 2 pi. 2 pi into that, and bandwidth is equal to, okay, no, there is a mistake here. So I can do it here. So bandwidth is equal to omega naught divided by Q. So this is omega naught divided by Q factor is R over L. So the Q factor is omega naught R over L. So it is omega naught R divided by L. So this cancels, and I have 1 nanohenry divided by R. So bandwidth is omega naught divided by Q, which is omega naught divided by omega naught R over L. Something wrong here. Okay, let us first find the Q. So from that question, the Q is equal to omega naught R over L, and that is equal to 2 pi 3 multiplied by 10 to the power 9 multiplied by 1 divided by L over R, sorry, L over R. So multiply 1 nanohenry divided by R. So this comes out to be 18.85. And bandwidth over omega naught is equal to 1 over Q, which is 1 over 18.85. Sorry, divided by 18.85. So this comes out to be 1 multiplied by 10 raised to the power 9 radians per second. So Q equal to 18.85, and bandwidth is equal to omega naught divided by Q, That will be 2 pi multiplied by 3 multiplied by 10 to the power 9 divided by q, which is 18.85. This comes out to be 1 multiplied by 10 to the power 9 radians per second. And if we convert it to frequency, delta f or bandwidth in terms of delta f, this is divided by 2 pi. So this comes out to be 0.16 gigahertz as we found in the question. All right. Okay, so now the last topic on this, well, the on the lecture, on this in this lecture, we will, as we always do with the filters, that whenever we discuss a circuit, we also discuss the transmission line equivalent. So luckily for also for the resonators, we have a very nice equivalence of transmission line. So let me just, what I will do here is I will show you those equivalents. So let us look at 4 equivalent circuits. We are not going to go into the proof. So I have lambda by 2 short circuit. I have lambda by 2 open circuit. I have lambda by 4 short circuit, and I have lambda by 4 open circuit. So I have 4 of these circuits. So lambda by 2 open circuit is like this. I have open, and the length is lambda by 2. The input impedance of this is equal to this transmission line has an impedance of Z0 and an attenuation of alpha. This is the attenuation which we, in the first lecture, we didn't actually, we ignored it after that. But in the resonator, we need that because we need the resistance. So this input impedance is given by Z0 divided by alpha L, which is the length of the transmission line, plus J delta omega pi divided by omega naught. Lambda by 2 short, it is like this. This is the circuit. So the length is lambda by 2. And the impedance here is Zn is equal to Z0 multiplied by alpha L plus J delta omega pi divided by omega naught. For the short circuit, it is lambda by 4. So it's a smaller line, lambda by 4. And the input impedance is like that. But the only difference is there is a 2 here. So Z input is equal to exactly the same. Z0 divided by alpha L plus J delta omega pi divided by 2 omega naught. So it is very close to this. The only difference is the 2. And the last one is the lambda by 4. So it's a smaller circuit, sorry, and there is an open here. And the length is lambda by 4. And the input impedance is again very similar to this, except there is a 2. So there is a Z0. I can just multiply it inside. So it will be alpha L plus J delta omega pi divided by 2 omega naught. So these are the 4 circuits, and if we look at the input impedance of the resonance, and I can make them equal. If you look at it for the series inputs, the series circuit, the input impedance is, as we found just few minutes ago, was R plus 2 J2 delta omega L. So what I need to do is I need to look at these circuits and find out which is the closest formula. So as you can see that this is Z0 divided by plus, real plus imaginary. So this is not the case. Also this is not the case because this is in the denominator. So we can have an open circuit, a short circuit lambda by 2 or an open circuit lambda by 4 to make the equivalent of this circuit. So what I do is I can have a lambda by 2 short short circuit. So the input impedance is this. We can make these two equal. So Z in equal to Z in. Both Z in are equal. Z naught alpha L plus J Z naught delta omega pi divided by omega naught is equal to R plus J2 delta omega L. So this R is equal to Z naught alpha L, and uh, uh, 2 delta omega L is equal to Z naught delta omega pi divided by omega naught. So delta omega cancels. So my L or Z, Z naught is equal to omega naught 2 omega naught L divided by pi. So Z naught is from here, it comes from here, and R comes from, sorry, alpha, because I need also alpha. Alpha is equal to from here. I calculate Z naught and then I put it here. So it will be R divided by Z naught and multiply by the L, which is the length of the transmission line in meters. All right. So I can prove it that this is correct by just applying these rules and finding the impedance, and then I can just put it into the nsoft and I can find the equivalent. So if you look at the next page, example 2, in which I need to find the equivalent circuit of the circuit which we did before. So I can, so this is the example 2. So the previous resonator, I can find the, let me just delete this because we are not using these two. So what I can do here is, I have this circuit. This is 1 nanohenry, and this is 2.814 pico. I need to find the the impedance of the short. So Z naught will be 2 omega naught, which is 3 gigahertz. So 2 multiplied by 2 pi multiplied by 3 multiplied by 10 to the power 9 multiplied by L, which is 1 multiplied by 10 to the power minus 9 divided by pi. So pi is pi here. Pi cancels with this, and this is, these two cancel, so it will be 3 multiplied by 2 multiplied by 2. So this will be 12 ohms. So this transmission line is 12 ohm, and alpha L is equal to this R over Z naught L. So this is 1 over 12 multiplied by L. Now what is the L of this? This is lambda by 2. So L should be equal to lambda by 2, which is equal to C over 2F, right? So this is 3 multiplied by 10 to the power 8 divided by 2 multiplied by 3 multiplied by 10 to the power 9. So this comes out to be 0.05 meters. So I just, my alpha will be R divided by Z naught L, so 0.05, and this comes out to be 1.66 Napier per meter. So now I have both of these 12 and alpha equal to 1.66. I can just put it in the nsoft, and this is coming in the homework which I promised you I will give you. So that homework in which you have to do these exercises. So, but the only thing is, if you look at the, go to the next page and you will see that, okay, one more thing is, what's the impedance will be divided by, so this is divided by 2, as you can see. So this will be multiplied by 4. So for this one, for this line, alpha equal to 1.66. So for this line, this is an open circuit, and the length is lambda by 4. Now lambda by 2 is 0.05. So what is lambda by 4? So length will be equal to lambda by 4, which is equal to half of this. So it will be 0.025, which is 25 millimeters. All right. Now in the impedance of this will be equal to, the only difference is because this is this exactly same except there is a 2 here. So this 2 will make this 4. So the impedance will be 24 ohm, and alpha will be same. No, alpha will be because yeah, there is a L here. Yeah, alpha will be same, but uh, yeah, alpha will be same because Z naught is double and this will be half. So alpha will be same. Alpha will be 1.66. All right, because from here, if you double this and this is half, so actually this will be same. And if you look at the NSoft simulations which I did on the last page, I have a short-circuited transmission line of length 50 millimeters. And the only thing which is new here is A in the NSoft. So this A in the NSoft is related to alpha is equal to 1.66. Now in the NSoft, I have this transmission line. I have this as 12 ohm for this. So I have this as a, for this I have an open circuit. So I have a transmission line open circuit, nothing here. So this is 50 ohm, sorry, not 50 ohm, this is 12 ohm transmission line, and the length is 50. If you double click on this, I will get this menu in which I have the length, I have impedance, and I have something called A. Now this A is this alpha, but in terms of 10 log. So A is equal to 10 log e raised to the power minus alpha. Sorry, minus, it is minus 20 log. So when I put it here, it comes out to be, I think, minus 14.5. So this is what you can see here. It comes out to be 14.5. So I put 14.5 here. But another very important thing is the frequency. The frequency should be 3 gigahertz. If you, and also if I connect the second port, because this is one port, so if I want to take the output, I need to connect the second port. So if I want to use it as a filter, I need the second port. So this second port, so I have now the circuit which is RLC, it's grounded, and line open circuit. But Z of this, Z naught should be 12, and the length should be lambda by 2. In this case, it is 50 meter. It equal to lambda by 2. And A should be equal to 14.5. This is dB per meter. This is NP per meter, Napier per meter, and this is dB per meter. So when the output of this, the V naught, and if I put this, it will exactly look like same. And you can just prove it by putting in the transmission line. And this is also lambda by 2. But this is equal to an open circuit lambda by 4. This is exactly equal to an open circuit, but with the impedance of 24 ohm, and A is same 14.5. But the length is, in this case, it is half of it, so it is 25 meter, which is equal to lambda by 4. So the resonances, and you can look at both of the circuits, lambda by 2 and lambda by 4, and I have the same results because those two circuits are actually equal. Okay, so this is the end of the lecture. Now what we have to do is I will give you the 10 mark there is one thing, the exam, the test, small test on the NSoft, which will be on Sunday. and inshallah we'll communicate on WhatsApp to decide the time on Sunday, or I can also move it to Monday. That's fine. That will be from the project on the filters. All right, the test on the unsolved, and there will be a homework which is 20 mark. I told you before, 15 mark. That will be on, some of the questions will be from the filters and some of the questions will be from the resonance circuit. All right, plus unsolved. So from that there will be a quiz, 5 mark, which will be useful for you in your coming career, especially related to the filters, the related to transmission. We couldn't do the whole course actually. It's almost 60-70% of the course because of the you know the, the, the circumstances we went through the semester. But I tried to give you some of the projects. You can do your own projects. I gave you this software, which is very very nice software. You can do a whole lot, design. All right. So thanks a lot, and inshallah we'll see you uh, later on. Assalamu alaikum.